Hello everyone, welcome back to the online lecture series of fluid mechanics, and we have completed with the first module, which is fluid properties. In the first module we have discussed the various fluid properties such as mass density, weight density, specific gravity. We discussed about viscosity and the associated property of dynamic viscosity and kinematic viscosity. Then we have seen that the fluids can be classified into two types, Newtonian fluids and non-Newtonian fluids, on the basis of the Newton's law of viscosity. Then we discussed about the interfacial phenomena of fluids and again the associated property of surface tension, which have many consequences such as the capillarity effect or the energy minimization principle or the pressure difference in case of curved liquid interface. Finally, we discussed about Weber pressure, and today we will start with the next module, which is fluid statics. Now, in this module, we will be discussing the forces that will be acting on the fluids at rest, and the state of rest may be studied under two heads. First is the fluids at absolute rest, and the second will be the fluids at relative rest. Now, by absolute rest, we mean that both the fluid as well as the container will be at rest or will not be in motion. So, both the fluid and its container will be at rest. This is what we call as fluid at absolute rest. Now, fluids at relative rest. By relative rest, we mean that the fluids will be at rest. However, the container which is containing the fluid will be in motion. So, together we will study the fluid and container as a rigid body, or we will study the rigid body motion. So, in this case, we have fluids at rest, but the container will be in motion. So we will say that there will be a rigid body motion studying the fluid and the container together. Now, before starting this chapter, let me give you a brief overview of the entire topic or the entire module. Here, in this, we primarily deal with the forces which are at either at absolute rest or relative rest, and the fluid property which is responsible for these forces is actually the pressure, which is the normal component of surface force per unit area. Now, we will start first with the necessary condition. We will first discuss about the necessary condition for a fluid to be at rest. So what will be the necessary condition for fluid to be at rest, and then discussing about the forces that will be acting on the fluids at rest, we will have a detailed discussion on various topics such as pressure, absolute pressure, and gauge pressure. We will discuss about atmospheric pressure, we will see the pressure acting at a point in a fluid at rest. Then we will see the variation of pressure with depth under the action of gravity. Thereafter, we will see the various pressure measuring devices. So, pressure measurement devices, which shall include the barometer, manometer and the various types of manometers. Then we will have a discussion on pressure gauges and some other methods to measure pressure. Now, after discussing this, we will move forward and we will discuss about the hydrostatic forces that will be acting on submerged bodies. The submerged bodies shall have a plane surface or a curved surface. So, the next, after this, we'll discuss about the hydrostatic forces on submerged bodies with plane or curved surfaces. After this, we will see the buoyant force that shall act on floating bodies, and we will discuss about the buoyancy. We will discuss about buoyancy and the related effects such as the stability of the body under these conditions, stability of bodies. And finally, under this head, fluids at relative rest, here we will be applying the Newton's second law of motion to a body of fluid in motion that acts as a rigid body, and analyze the variation of pressure in fluids that undergo linear acceleration or in rotating containers. So these are the topics which we will be discussing in both these heads. Now, you may think of the various applications of fluid statics, or what are the various applications or uses of fluid statics. So, let me discuss about those. Using the principle of fluid statics, we can compute forces on submerged bodies, as well as we can locate the point of application of the forces on bodies such as, say, dams, ships, or submarines. We can also use the principle of fluid statics to develop instruments for measuring pressure, or we can also use them to deduce the properties of the atmosphere and oceans. Now, the principle of fluid statics can also be used to determine the forces that are developed by hydraulic systems in applications such as industrial presses or automobile brakes. So, now let us start with our module in detail. Now, recalling our definition of fluid, we may recall fluids as substances that deforms continuously under the action of a shear stress, and it is this continuous deformation over time which constitutes a flow. So, we have already defined fluids are those substances that deforms continuously under the action of a shear force, and this continuous deformation is what constitutes a flow. But when we talk about fluid statics, it means that the fluid is at rest or the fluid is not in motion, which according to our definition will only be possible when there will be an absence of shear force. So a fluid is said to be at a state of rest, or a static fluid implies it implies an absence of shear force or shear stress, an absence of shear stress, or you can say that there is no angular deformation, no angular deformation, or there is no relative motion between the layers of the fluid, no relative motion between the fluid layers. So the necessary condition for the fluid to be at rest is the absence of shear force or shear stress. Now in such a situation, when there is an absence of shear stress, what are the forces that will be acting on the fluid? Now under these conditions, the only forces that will be acting on the fluid shall be forces acting will be first will be the body force, or simply we can say that the weight of the fluid element, weight of fluid element under the action of gravity, under the action of gravity. And the second will be, since we have already omitted the shear stress or the shear force, the second type of force that will be acting will be the normal component of the surface force. So second is the normal component of surface force. If you recall, during our discussion about the fluid definition, we have seen this, that if this is an arbitrary fluid element and we have a small force, say dF, that is acting on a small area, say dA, we shall resolve the force into its two components. And the two components were, first was the component which is acting parallel to the surface, and the second component was the component which was acting perpendicularly to the surface. And the component which we are talking about, or which is perpendicular to the surface, was denoted by dFn, and the component of the force that was acting parallel to the surface was dFs or dft. Now this is the shear force which we are talking about, shear force, and this is the normal force. In terms of stress, we will say that the state of rest is say defined by the absence of shear stress, and the only stress that will be available to us under this condition will be the normal stress. Now this term normal stress is used primarily in case of solids. In case of fluids, the normal force per unit area is known as pressure. So the pressure means the normal component of the surface force acting per unit area of the fluid element. So let us now discuss pressure in detail. Now pressure is a measure of force distribution over any surface that is associated with the force. It is a surface phenomena, and it can be physically visualized or calculated only if the surface over which it acts is specified. So you can say that pressure may be defined as the force that is acting along the normal direction on unit area of the surface. So let us now discuss about pressure in detail. So pressure is actually, it is a measure of force distribution. It is a measure of force distribution over any surface, over any surface upon which the force acts, upon which the force acts. It is a surface phenomena. It is a surface phenomena, and it can be physically visualized or calculated only if the surface over which it acts is specified. So we need the surface to be specified, then only we can calculate the pressure. In simple terms, pressure may be defined as the force acting along the normal direction on unit area of the surface. And a more precise definition of pressure will be P is equal to limit A tends to small a, we have pressure is force acting per unit area. So del F upon del A, or in higher terms we'll say dF upon dA. Here P is what we call as pressure, or in a more accurate term we will say that this represents the intensity of pressure. So this is the intensity of pressure. Here the small a represents the limiting area which will give us result which is independent of the area. So small a represents the area, limiting area. A, we can say that it is the limiting area which will give us the results that is independent of the area, which will give us results independent of the area. So the force dF is the normal component, is in the normal direction on the elemental area dA due to the pressure, and it may be calculated as dF is equal to the intensity of pressure P into dA. So the force due to pressure may be calculated as the intensity of pressure into the area upon which the force or the pressure is acting. Now the unit for pressure, the SI unit of pressure will be, for force we have Newton and for area we have meter square. So the SI unit of pressure is Newton per meter square. So let me write it down. So SI unit is Newton per meter square, or it is also known as Pascal. So we will say that 1 Pascal is equal to 1 Newton per meter square. Now this is a very small unit, and generally we use higher units, for which we use say 1 kilopascal. 1 kilopascal represents 10 to the power 3 Pascal, or 10 to the power 3 Newton per meter square. A more higher unit is 1 megapascal, which is actually 10 raised to the power 3 kilopascal, or you can say 10 to the power 6 Pascal, or Newton per meter square. Then we have the unit for atmospheric pressure. For atmospheric pressure, the pressure 10 to the power 5 Pascal is what we call as a bar. So for atmospheric pressure we have the unit used is 1 bar, and 1 bar is 10 to the power 5 Pascal. Also we have one more unit for atmospheric pressure, that is ATM. So 1 ATM is actually equal to 101,325 Pascal, which can be written in terms of kilopascal as 101.325 kilopascal, or 1.01325 bars. Now there is one more unit for atmospheric pressure which is generally used, and we say it 1 kilogram force per centimeter square. Now what is this 1 kilogram force per centimeter square? It is equal to 9.807 Newton per meter square. Sorry, Newton per centimeter square. Or in terms of Newton per meter square, we will say that this will be equal to 9.807 into 10 raised to the power 4 Newton per meter square. In terms of bar, it will be 0.9807 bars, and in terms of ATM, it is equal to 0.9679 ATM. 0.9679 ATM. So these are the various units of atmospheric pressure that we will generally encounter in various numericals that we will be solving. Beyond this, we have some more system of units such as the British gravitational units, and in British gravitational unit, the most common unit is PSI, which stands for pound force per square inch. Now this pound force per square inch in 1 ATM is actually equal to 14.696 psi. 14.696 psi. So an atmospheric pressure in terms of psi will be equal to 14.696, and also 1 kilogram force per centimeter square, this will be equal to again 14.223 psi. 14.223 psi. Now these are the various units that we will be using for pressure, and it is important to know all these values because it will be helpful for conversion in case of numerical. In numericals we get the different values of pressure. You might have seen this PSI when you have when you go to say when you go to inflate your tires in your bikes. This PSI is generally what we find out in the pressure gauge that is used by the mechanic. So this PSI stands for pound force per square inch. Moving forward, we have various scale of measurement of pressure. So let us now discuss about the various scales of measurement, and here we will see the different types of pressure, different kinds of pressure, namely the absolute pressure and the gauge pressure. So let us see the various scales of measurement of pressure. To understand the various scales, we will use a diagram, and through which we can easily understand the various scales. So the scales of measurement. Now this is the baseline, which represents P is equal to 0. It means it is a zero pressure line, or you can say this is actually, we will when we talk about absolute pressure, this is P absolute is equal to 0, because absolute pressure is the actual pressure at a given position, and it is measured relative to absolute vacuum. So this is also known as absolute vacuum pressure. Absolute vacuum. Now let us, we already know about atmospheric pressure. The value of atmospheric pressure PATM is 101.325 kilopascal. So let us say that this line represents atmospheric pressure. So this is your P atmospheric. Now if the pressure lies above the atmospheric pressure, so we can represent it by this line. In this case, see, the absolute pressure is measured with respect to the absolute vacuum or zero pressure. So if we draw an arrow up to this point, this arrow shall represent the P absolute. Similarly, this is P atmospheric, and it is also measured with respect to absolute vacuum. So this will be your P absolute is equal to P atmospheric pressure. So this is P atmospheric. Now when the absolute pressure is measured with respect to the atmospheric pressure, we call it the gauge pressure. So, or in terms of P absolute and P atmospheric, we will say that the difference between the absolute pressure and the atmospheric pressure is what is referred to as the gauge pressure. So in this case, what will be the difference? P absolute minus P ATM. So this is what is referred to as the P gauge. Actually, this is the positive gauge pressure which we are talking. Now, if the pressure is lying below atmospheric pressure, let us say that this is the absolute pressure, this will be the absolute pressure, and in this case also this will be your atmospheric pressure. Now P atmospheric, P absolute minus P atmospheric is what we have already defined as the gauge pressure. In this case, we draw P absolute minus P atmospheric will be negative because P atmospheric is greater than P absolute. So we will denote it by using a downward arrow. So this becomes our P gauge, which is actually the negative gauge pressure. So now we can define the various terms. Absolute pressure, absolute pressure is the actual pressure that is measured relative to the absolute vacuum or the absolute zero pressure, and this is what we call as the absolute pressure. Now, most pressure measuring devices, however, are calibrated to read zero in the atmosphere, and so they indicate the difference between this absolute pressure and the local atmospheric pressure. And the difference between the absolute pressure and the local atmospheric pressure is what is referred to as the gauge pressure. So, absolute pressure is the actual pressure measured relative to the absolute zero pressure or absolute vacuum pressure. And secondly, we have the gauge pressure. So gauge pressure is simply the difference between the absolute pressure and the local atmospheric pressure. Now this gauge pressure is of two types, as we have already discussed. First is the positive gauge pressure. So when we have P absolute greater than P atmospheric, then the difference P absolute minus P atmospheric is what is called the positive gauge pressure. Now secondly, when we have P absolute less than P atmospheric, then in that case what we will get a negative value. So we will say that P, in that case, P atmospheric minus P absolute will be the P gauge. Now this is the negative gauge pressure, and this is also known as the vacuum pressure. So these are the scales of measurement which are very important, and you must remember that most of the pressure measuring devices are calibrated to read what they take the difference between the absolute pressure and the atmospheric pressure. So most pressure measuring devices gives us the gauge pressure. So whatever readings we see in the various devices, we actually see the gauge pressure. So in case if you are asked to find out absolute pressure, you must find out the difference between the absolute pressure and the atmospheric pressure.